Hi folks, I'm Adam, your instructor. Welcome to the Laney College Machine Shop. Today, we're going to be working on the Finder Scope project for Machine Tech 210, the introductory course in machining and manufacturing. Specifically, we're going to be working on the upper piece of the adjustable altitude-azimuth mount. We're going to take this 3/4 of an inch by 1 1/4 of an inch by 3 1/8 of an inch aluminum block and turn it into this part, doing all the millwork. Before we get started on the machine, let's just take a few moments to review the features on the three-dimensional solid model and the specifications on the drawing. The three-dimensional solid model shows that this part is very similar to the other two mill parts we've made. The part is more or less a rectangular prism with steps on both sides and a large V-groove going through the center. There are a couple of counterbore holes, and it should be noted that the counterbore features themselves are on opposite sides of the part. The hole in the step has the counterbore on the top of the part, whereas the hole which goes through the V-groove has the counterbore on the bottom of the part. So this will require flipping the part when drilling those holes. Finally, there are 4 threaded holes for the screws, which will fasten to one side of the flexure that will be the pivot for the altitude or up and down adjustment of the mount. Alright, here's the drawing. Before we jump into the views, let's get a lay of the land. Down in the title block at the bottom right, we can see that the title of the part is Mount Upper. Next to that, on the left, we can see that the material is going to be 6061 T6 aluminum alloy, and the finish is going to be fine bead blast. Further to the left, you can see the tolerance block, which specifies our standard shop tolerances for the different dimensions on the print where no other tolerance is specified. These are all based on significant digits, so the number of places after the decimal point determines the tolerance of that dimension. We'll also be looking for a standard 125 micro-inch finish on all of the surfaces, and we're going to interpret everything on this print according to ASME Y14.5-2018, the most recent standard for print specifications. Okay, looking at the views themselves, we can see that we've been given one of those isometric views of the part for our reference, and we're given 3 orthographic projection views, what I would call a front view, a top view, and a left side view. The front view is also a section view, and you can see the cutting plane line that generated it in the top view. It looks like the top view was sliced right down the middle from left to right. So in the front view, we're looking at the half of the part that the arrows on the cutting plane line are pointing toward. This explains why there's a region where there are no section lines on the front view. It's because there we're looking at one of the inclined planes of the V-groove, which wasn't intersected by the cutting plane. The section view is really helpful for understanding the orientation of the counterbore holes. There are a bunch of dimensions which specify the sizes of various square-sided features and the locations of the holes. There are also some special hole notations which specify the sizes, depths, etc. of the features on those holes. On the left side view, the V-groove has an angle dimension and some associated linear dimensions specified in a very interesting way, which makes reference to a measurement device called a gauge pin, but more on this in a bit. Let's try to get a sense of the overall dimensions of this part so we know what we're dealing with. It looks like the overall depth of the part is 1 inch 250 thousandths, or 1 1/4 inch, and the overall height of the part is 750 thousandths, or 3/4 of an inch. As before, both of these are stock dimensions provided for reference only. The raw material we'll use for this part is 3/4 of an inch by 1 1/4 inch extruded aluminum, and the drawing is telling us we're going to leave these dimensions alone. However, we will need to finish the width dimension, because this is what we'll cut off on the bandsaw. That overall width will be 3 inches. Notice that this dimension is not in parentheses or labeled stock because we will need to machine it. Hopefully, this helps you get a sense of the size of the part you should be imagining in your head. Okay, looking at the dimensions a little bit closer now, we can see that the steps will have a height of 375 thousandths of an inch. Notice that this is not specified as the height of the step itself, but rather as the height, or like the thickness perhaps, of the material left behind. And it's dimensioned to 3 decimal places, which means it will have a tolerance of plus or minus 5 thousandths of an inch, according to the tolerance block. This is something to pay attention to. The steps will have a width of 1 inch, although you can see that this dimension is only specified for the step on the left side. This is to reduce clutter on the drawing, but also to eliminate what's called tolerance stacking. That's just the idea that all the width dimensions need to add up to the overall width dimension. So we know the width of the step on the right side has to be 1 inch. But you don't want all of those dimensions and their respective tolerances fighting each other. The width of the step on the right side will just be whatever it ends up being after we cut the features and the dust settles. Speaking of width dimensions, the width for the V-groove region in the center is also 1 inch, but specified with 3 decimal places. So again, something to pay attention to. There are 2 counterbore holes. The first one goes through the top of the part on the right side step. It will be located 2 inches 380 thousandths from the left side and is on center of the part in the 1 inch 250 thousandths depth direction. This hole will have a diameter of 188 thousandths and go all the way through the part, and the counterbore will have a diameter of 320 thousandths and a depth of 130 thousandths. The second hole goes through the bottom of the part in the center region with the V-groove. It will be located 1 inch 500 thousandths from the left side and is also on center of the part in the 1 inch 250 thousandths depth direction. This hole will have a diameter of 281 thousandths and go all the way through the part, and the counterbore will have a diameter of 410 thousandths and a depth of 250 thousandths. Notice the backside notation next to the counterbore specification, which indicates that the counterbore should go on the side of the part opposite the side where the hole is specified. Since the hole is specified in the top view on the drawing, the backside would be the bottom of the part. I mean, we already figured this out in other ways, but just to say that this is another way to know the orientation of the counterbore hole. Just as on the mount intermediate part, there are the 4 holes shown in the left side view. These will have a diameter of 107 thousandths with a depth of 400 thousandths. They will also have number 632 UNC 2B screw threads with a depth of 300 thousandths minimum. The holes are located 281 thousandths relative to each other, and the row of holes, the entire hole pattern, appears to be centered on the part in the depth and height dimensions. Okay, the last thing to look at on this drawing is the V-groove. The angle of the V-groove is specified as an included angle, meaning the angle between the 2 sides of the V of 120 degrees. The tolerance block indicates that the tolerance for this angle will be plus or minus 1 degree. Not terribly difficult to accomplish, but again, we'll need to pay some attention to this. As for the location of the V-groove, it looks like it needs to be on center of the part in the 1 inch 250 thousandths depth direction. So far so good, but the height dimension of the V-groove is a little bit trickier. Since the sides of the V-groove are not square to the rest of the part, there are no parallel surfaces to which you could measure with a dial caliper or a micrometer. In theory, you could measure to one of these corners on the bottom of the part, but those would not be reliable features to use as references, because in practice they will always have either a burr or a chamfer on them. So one common way to measure a feature like this with angled surfaces is to put a gauge pin, that is a precision ground steel cylinder with a known size, in it, and then measure over that relative to some opposing flat surface, in this case the bottom of the part. Calculating the height where the top of the gauge pin is supposed to be is pretty straightforward, but here it's provided for you on the drawing as 1 inch 230 thousandths. 2 decimal places, plus or minus 10 thousandths of an inch, so not really a very tight tolerance at all. There's also another height dimension specified here, 424 thousandths, which is the height from the bottom of the part to the intersection of the two V-surfaces. This dimension is in parentheses, indicating that it's a reference dimension only. We will be using this dimension to make the V-groove, but it's not a dimension that is easy to inspect, which again is why the height of the V-groove was specified another way, using the gauge pin method. Okay, that's it for the print. Nothing on here should really be surprising to you by this point, with the exception of the V-groove feature. Anyway, I think we're ready to start making some chips, so let's head out to the shop. And let's start by gathering up some tools. We'll need a 1/2-inch high-speed steel end mill, a 5/16 high-speed steel end mill, a No. 4 high-speed steel center drill, a No. 36 high-speed steel twist drill, which has a diameter of 107 thousandths, a 3/16 of an inch high-speed steel twist drill, a 9/32 of an inch high-speed steel twist drill, a 1/2-inch high-speed steel countersink with an included angle of 90 degrees, a No. 632 tap with spiral flutes, and a high-speed steel counterbore for a 1/4-inch screw. And that's it! Let's hop straight onto the mill. I've already got a mill vise set up, and we'll need some parallels. I believe these are 1 1/8 of an inch. Now, I already cut the stock material on the bandsaw, but I forgot to shoot video of it. You don't really need to see me do that again, do you? I don't think so. But just remember that this is the 3/4 of an inch by 1 1/4 inch 6061 T6 aluminum rectangular bar, and we're cutting off a 3 1/8 of an inch long piece. The material goes into the mill vise on top of the parallels with about a 1/2 inch of stick out from the left side of the vise. And now we need the 1/2 inch high-speed steel end mill, which will be held in a 1/2 inch R8 cullet. This is going to be a familiar song and dance to you. We're going to touch off on one side of the part, zero the digital readout, and then take a cleanup cut of about 10 thousandths of an inch. Then I'm going to remove the part and deburr the edges. Flip the part around and put it back in the mill vise with that same 1/2 inch stick out, touch off, zero the digital readout, and then take a cleanup cut of 10 thousandths of an inch. Now that I've got nice machined surfaces on both sides of the part, I'm going to measure over it with a dial caliper, and this looks like 3 inches and 40 thousandths of an inch. So I'm going to enter this value for the x-axis on the digital readout. Then I'm going to take 2 more cuts to get down to our final size of 3 inches. A final measurement shows that we are right where we want to be, so that's great. Alright, I'm going to remove the part and deburr the edges. Now that we've cut our stock material to the correct overall dimensions, before we continue on with the next machining operations, we need to do some layout to help guide us in the next steps to make the V-groove. So I'm at a workbench, and I'm going to shake up this bottle of layout fluid and apply it to one of the ends of the part that we just machined. And then I'm going to let it fully dry. And I do enjoy watching this sped up footage of the paint drying. I know it's a little ridiculous, but there's something kind of satisfying about it. Alright, onto the surface plate, and we're going to need that height gauge with the Scribe attachment again. Go ahead and turn it on, and then touch the Scribe off on top of a 2 thousandths thick shim. Then zero the readout, go down another 2 thousandths of an inch, the thickness of the shim, and then re-zero. Now that we zeroed the height gauge, all of the heights that we set will be from the top of the surface plate as the reference. So that's what we want, so we can begin layout. The first thing that we're going to lay out here is the point at which the two V surfaces intersect. So we'll need to lay out 2 lines. The first one will be at 424 thousandths from the bottom of the part, and the other one will be on center of the part in the 1 inch 250 thousandths depth dimension. So I'm going to raise the Scribe up 424 thousandths according to the readout, and then scribe a line in the center of that surface. Then I'm going to flip the part 90 degrees and raise the Scribe to 625 thousandths, which is half of 1 inch 250 thousandths. Then I'll scribe that line in the center of the surface. And this is what it should look like up close. Now the question is, how do we get those V surfaces in there at the correct angle? There are many ways to do it, but this time we're going to use a special V block. The two V surfaces on this inspection tool have an included angle of 90 degrees. But hopefully you can see that the entire V feature is kicked over a little bit. It's not square, it's not symmetrical on the two sides, it's kicked over a little bit, and it happens to be exactly 30 degrees relative to the bottom of the V block that's sitting on the surface plate. So when we stick the part into the V block, the two sides of the part will be touching the V surfaces, but the entire part will be kicked out at that 30-degree angle. Since the included angle of the V groove on the part is 120 degrees, that means that the angle between either of the V surfaces relative to the bottom of the part is going to be 30 degrees. So if we scribe two lines at 30 degrees from the bottom that meet in the middle, the included angle between those two lines will be 120 degrees. And that's what we're going to do here. And we're not going to do this numerically, so I'm just going to go ahead and shut off the digital readout on the height gauge. Instead, I'm going to visually align the very tip of the scriber to the intersection of those two lines that we've already laid out. Because of course, this is where we want the lines for the V groove to intersect as well. I'm going to scribe that line all the way to the edge of the part. Then I'm going to rotate the V block and flip the part to the other side so that it's sitting the other way. And I'll scribe that part from the edge to the intersection. When all is said and done, it should look something like this. Okay, we're back on the mill, and we're going to put the part down on the parallels with the laid out side against the movable jaw of the vise, so facing toward us. But we're not going to put the part down square to the parallels. Instead, we're going to tip it up at an angle, just trying to line up those scribed lines to the top of the movable jaws. So only the corner, the bottom corner of the part should actually be touching the parallels. And then we'll close the vise jaws, but only very loosely, because we still need to set the angle of the part more precisely. And this is the tool that we'll use to do it. This is called a digital angle gauge, and it is your friend. The first thing that we need to do is set the gauge to 0 on a flat reference surface which is square to the machine. The top of the vise will do just fine, so go ahead and turn on the gauge, clean off the top of the vise, and then set the gauge down on the top of the vise, pushing it against the back of the fixed jaw so it's sitting square to the machine. Then press the set button to zero out the gauge. Then place the gauge on top of the part, doing your best to keep it as square as you can. Now, these angle gauges do have magnets in them, but unfortunately aluminum is non-magnetic. So you're going to have to hold the angle gauge against the top of the part with one hand. With the other hand, you're going to loosen the vise jaws a little bit, and then tip the part until it's sitting at 30 degrees according to the angle gauge. Then tighten the vise jaws back. This is what it's going to look like when everything is in place, and you can see that that scribed line is very, very parallel to the top of the vise jaws. If it doesn't look parallel on your part and in your setup, then there is something wrong, and you should stop and evaluate. One of the possible issues, which I'll just mention straight away, is that the bottom of the angle gauge has these sort of two contact pads on either end with a recessed area in the middle. That recessed area is just big enough to straddle the top of the part. But if you're off-center a little bit, then of course you're going to be partially on the recessed center section and partially on one of the pads, and you'll be cocked out at an angle which will give you an incorrect setting on your part. Just a little nuance to keep in mind. Okay, and now we can take some cuts. No need to use the digital readout here. We're just whittling away at this material until all of the surfaces look like they're lined up to those layout lines by eye. Here you can see I'm bringing the tool down a little bit, just trying to stay away from those layout lines while I'm roughing this thing in. But I'm using the conventional milling technique to remove this material for reasons that we've already discussed in other videos. Just trying to get rid of all the material up close to those layout lines. Then go in for the final cut, touching that intersection on the right side and touching the layout line on the bottom. Okay, after cleaning those chips off, this is what it should look like. Again, what you want is for the vertical surface to line up with the intersection of all those layout lines on the right side, and for the horizontal surface to just touch the horizontal layout line. And this is looking pretty good. So I'm going to remove the part, clean off the jaws and the parallels, then stick the part back in, and go through this whole rigmarole one more time. Zero the gauge, stick it on top of the part, tip the part to get to 30 degrees, then tighten the vice jaws again. Okay, this side is going to be a lot easier to rough out because most of the material's gone already. And then 2 finish cuts is all it should take. And this is what it should look like. Again, the horizontal surface is just touching the horizontal layout line, and the left side of that surface is touching the intersection of all of those layout lines. Now, I may have made that process look a little bit too easy. There was a fair amount of fiddling that I did off camera that didn't make it into the cut for the final video because it was frankly kind of boring. But I was really taking special care to make sure that I didn't overcut those layout lines. I took some smaller test cuts and really got in there with a magnifier to make sure that everything lined up before I committed and took all of the material off. And you should exercise the same level of care when you do yours. It's always easier to take more material off than it is to put it back on. Okay, but we still need to measure the V-groove to make sure it's in tolerance. So grab a 3/4 of an inch or 750 thousandths gauge pin. Set that into the V-groove, and then we're just going to measure between the top of the pin and the bottom of the part using a dial indicator, because the tolerance is only 2 decimal places, and that'll be just fine. This is looking like 1 inch 235 thousandths, and the target dimension according to the drawing was 1 inch 230 thousandths, so we're only 5 thousandths off, which is pretty good for doing it by eye, I think. Anyway, it's within tolerance, so let's move on. Now we can remove the part and remove the parallels, and we'll need some taller parallels. I believe these are 1 3/8 of an inch. I forgot to deburr the edges of the V-groove, so I will do that right now. And then I'm going to clamp the part in the vise with the bottom down on the parallels, roughly in the center of the jaws. And notice that the laid out surface is on the left side. I'm going to hammer down on the parallels so that they don't move, and then I'm going to install a vise stop. Okay, now I've positioned the part and rotated the spindle to align the cutting flutes of the end mill so that when I drop the quill down, the cutting edges will touch that thin surface that's left over on the top of the part. Now I'm going to zero the Z-axis on the digital readout right there. Bring the quill back up, move the part out of the way, drop the quill back down to 350 thousandths on the Z-axis. Then I'm going to turn on the spindle and touch off on the right side of the part. I'm going to zero the X-axis on the digital readout right there, and then I'll start taking some roughing cuts. This first one's at 200 thousandths, and then 400 thousandths, 600 thousandths, 800 thousandths, and finally 990 thousandths. This should leave us enough material for a 10 thousandths finish cut on that 1 inch width of the step. But that 375 thousandths height dimension was specified to 3 decimal places, so we'll take a little bit extra care with that. We'll measure it with a micrometer and then remove whatever material we need to based on that measurement. This is looking like 401 thousandths. So I'll go ahead and set the Z-axis on the digital readout to this value. Then I'll drop the quill the rest of the way to the finished dimension of 375 thousandths. I also moved in on the X-axis the rest of the way to 1 inch. A little WD-40, and then zigzag across the part to finish that feature. Let's take a final measurement with the micrometer, and yeah, 375 on the money. So that is wonderful news. Okay, let's take out the part and deburr all of those fresh edges. Okay, I'm going to clean the vice jaws and the parallels and then put the part back in, but rotate it 180 degrees so that the side that we just cut is now against the vice stop. Again, use a hammer to seat the part down on the parallels, and then I'll come and touch off on the side of the part just to make sure that it's still at 0, and it looks like it's really close, like 1.5 thou, not bad. You can also see that I raised the quill back up a little bit from 375 back to 400 thousandths. I'll drop it back down when we do our finish cuts. All right, a little WD-40, and let's take some roughing cuts. Same roughing cuts as before, 200, 400, 600, 800, and 990. Okay, now remember that the center region with the V-groove was specified as 1 inch to 3 decimal places, so we'll need to measure that with a micrometer as well, and then remove the material to get to the finished size based off of that measurement. Okay, this looks like 1 inch and 10 thousandths, which is exactly what it's supposed to be, because the last roughing cut was at 990, in order to leave a 10 thousandths finish cut, which is exactly what we've got. So this is behaving very predictably, which is great. I'm going to go ahead and set the x-axis to the measured value at this position. Then I'll move over and down to 1 inch on the x-axis and 375 on the z-axis, and then we'll take the finish cuts. A little WD-40, and away we go, zigzagging over that entire surface. Final measurement with the micrometer looks like, yeah, a half a thou over. It's great. All right, let's drop the knee and move the part out of the way because it's time to switch out tools. We don't need the end mill or the collet anymore, but we do need the drill chuck. And then an edge finder will go into that. First, I'm going to find the center of the part in the y-axis direction, and I'm actually just going to use the inside of the vice jaws themselves. It's really just as good as using the part surfaces directly. Then I'm going to go and find the left side edge. From there, I'm going to move to 2 inches, 380 thousandths, which is the x-axis position of the first counterbore hole. Switch out the edge finder for a center drill, and then spot the hole. Then we need the 3/16 of an inch twist drill, and we'll drill all the way through. Then we'll remove the drill chuck, and yes, I know this is a little bit tedious, and we'll put a 3/8 of an inch collet into the spindle. Into that will go the 5/16 of an inch end mill. Now bring the quill down to touch off the bottom of the tool to the top of the part. Zero the z-axis on the digital readout right there, turn on the spindle, hit it with some WD-40, and then plunge to a depth of 130 thousandths. Okay, we're done with the end mill and the collet, and now we need the drill chuck again. We also need to flip the part over, but before I do that, I'm going to deburr all of those edges that I didn't do before. Then I'll remove the parallels, clean off the vice jaws, and then put some shorter parallels in there. I believe these are 1 1/8. Okay, now I'm going to put the part back into the vise, down on the parallels with the bottom of the part facing up. Push the part up against the vise stop, making sure that the hole that we just drilled and counterbored is on the right side. Okay, we need a center drill again, and we'll move to 1 inch 500 thousandths on the x-axis, which is the position of the second counterbored hole. Spot the hole, and then we need the 9/32 twist drill. A little WD-40, and then we'll drill all the way through with this drill. Okay, now we need the counterbore, the proper counterboring tool, sized for a 1/4 inch socket head cap screw. Make sure the top of the part is clean, then drop the quill so that the bottom of the counterbore, the actual cutting flutes on the counterbore, are touching the top of the part. Zero out the z-axis on the digital readout right there, turn the spindle on, hit it with some WD-40, and then plunge to a depth of 250 thousandths. All right, clear that nasty bird's nest, and we're done with the counterbore tool. And we can also remove the part. Okay, before we move on, let's take a moment to deburr the backsides of all those holes that we just made. So go ahead and put the 90-degree countersink up into the drill chuck, turn the spindle on, and then bip the part into the countersink by hand, just to lightly deburr those holes. The countersink is not going to work for the center hole where it intersects the V surfaces, so we'll just have to do that by hand with one of those scraper deburrers. Alright, let's remove the parallels and clean the vice jaws, and then we'll put in some shorter parallels. I believe these are 7/8 of an inch. The part will go down on the parallels with the V groove toward the movable jaw of the vice, so facing you. The V groove should be in the vertical orientation, and the counterbored hole in the step should be down toward the parallels. Here's what it's supposed to look like up close, and just notice that the parallels we selected were enough to give us just a little bit of a gap between the center region of the part with the V groove in it and the tops of the jaws. Okay, we need the edge finder again, and I'm going to go ahead and find the center of the part in both the y-axis and x-axis directions. You should be a master at the edge finder and the digital readout by now. You have done this so many times. Okay, we're going to make the number 632 UNC 2B threaded holes now, and it's going to be exactly the same way that we did it for the mount intermediate part. But I did just want to reiterate that we're going to be positioning the holes based off of the center of the part. So we need to do some calculations in order to figure out what those positions are going to be. We know that the distance between two adjacent holes is going to be 281 thousandths. So the distance from center to one of the inside holes is going to be half of that, or roughly 141 thousandths. The distance from the center to one of the outside holes is going to be 141 thousandths plus 281 thousandths, so 422 thousandths. Let's go ahead and move to the position of the first hole now. Then take out the edge finder and put the center drill in. Spot the first hole. Then spot the second hole. Then spot the third hole. And finally spot the fourth hole. Now we can take out the center drill and put in the number 36 twist drill. Okay, I'm going to start by drilling into the part just a little bit. Then I'll stop the spindle and drop the quill down to visually align the point on the drill where the drill tip ends and the full diameter of the drill begins, and line that up to the top of the part. Then I'll zero the z-axis on the digital readout, turn the spindle back on, and plunge to the final depth of 400 thousandths. This is exactly the same way that we did it on the last part. Okay, that's hole 1 done. Let's move to the second hole, and then drill that to a depth of 400 thousandths. Then move to the third hole and drill that to a depth of 400 thousandths. And then move to the fourth hole and drill that to a depth of 400 thousandths. Okay, we're done with the number 36 twist drill, and now we need the 90-degree countersink. Turn on the spindle, take a light cut on the hole, and then measure it with a dial caliper. The countersink diameter should be about 30 thousandths of an inch over the major diameter of the screw threads, which is, for a number 632 screw thread, 138 thousandths. And this is looking pretty good. So with the spindle off, I'm going to drop the quill so the countersink is sitting back inside the top of the hole. Then I'll zero out the z-axis on the digital readout and move to the second hole. Turn on the spindle and plunge to 0, then move to the third hole and plunge to 0, and then move to the fourth hole and plunge to 0. Alright, last but not least, it's time to tap the number 632 threads. As before, you should exercise extreme caution and be hyper aware of any kind of resistance when tapping with these delicate little taps. It would be a crying shame to break off a tap at the very, very, very last step of this part. Anyway, once you've done the first hole, do the second hole, and then the third hole, and then the fourth hole. And when you've made it through the entire gauntlet, you can remove the tapping tool, clean off the part, and remove the part from the vise, because it's done! Look at this thing. What a cool little part. That V-groove came out great. The only thing that this part still needs is to get bead blasted, but all the machining operations are done. We are very, very close to the finish line for this project now. We just need to make it pretty and put it all together. The hard part is basically over. So if you successfully completed this part, hold your head up high and repeat after me. I am a machinist. Anyway, I'll see you in the next video. Thanks for watching.